Well, hey everyone, welcome back. This is the part 2 video of the single driven element Class A amplifier, where we're utilizing a constant current source and of course the driven element itself. If you haven't watched part 1 of this video, I would encourage you to go and do that so that this makes sense. Before I get into the circuit that I've come up with, I want to talk about the theoretical efficiency and how that's calculated, because I want something to compare the actual efficiency I get with the circuit that I build. And in my example, I want to use a 12-volt power supply. And because we go through the coupling capacitor, you can think of it as a +6 and -6 range that our sine wave is going to sweep through. So with a 12-volt power supply and no losses in our circuit, our signal is going to be able to swing from rail to rail, giving us 12 volts peak to peak. In other words, it'll be 6 volts peak or 4.2426 volts RMS. So we know the theoretical maximum RMS voltage output we can get from this amplifier with a 12-volt supply. And, well, that's pretty easy to calculate the wattage now. It's that RMS voltage squared divided by our 8 ohm load. We get 2.25 watts. Well, now we need to know how much the circuit is using in total. So to find the current, we need to set up our amplifier at quiescent. In other words, what our constant current source needs to be set for. We take the 6 volts peak divided by the load impedance of 8 ohms, and we get 0.75 amps, 750 milliamps. So why are we using this peak voltage here, not RMS? Well, at certain points in time, the waveform is going to be at its peak, and we have to be able to have that amount of current to be able to drive the load to that level. We're not going to be able to get our 4.24 volts RMS of output. So now that we know the current, we can calculate the total power consumption of the amplifier. Well, we know we have a 12-volt supply, and we know it's set for 0.75 amps. It's going to consume 9 watts. What is the efficiency? Well, it's our output power versus our total consumed power times 100 to convert it into a percentage. We get 25%. Now in the real world, with a real circuit, I'm not going to get anywhere near this because, we have emitter resistors, one's being a sense resistor, losses across the transistor, and other losses that will bring this value considerably lower. You might have heard that the theoretical efficiency of a Class A amplifier is as high as 50%, but we're using another element in the circuit, a constant current source that's going to soak up half the power, and it's going to take the efficiency down to a theoretical maximum of 25%. Well, it's a few days later, and through the magic of video editing, it seems like it just happened. But I'm back and I created this little circuit here. This is actually the load part of this current source. So I'm representing this current source as this symbol right here, and this is the load part of the current source. So what we have here is really just a Darlington circuit. So we feed our signal in here, and it goes through a couple transistor stages, giving us enough amplification to drive this voltage point here up and down. And of course we connect our load through the DC blocking capacitor because we don't want DC to pass through into our load. At this point, I will say one thing about what I said earlier with the efficiency. It was brought to my attention by somebody in the comment section that a guy named John Linsley Hood, if I remember correctly, he developed an amplifier that, a Class A amplifier that is actually more efficient. He modulated the current source with the input signal, and that allowed him to double his efficiency. He was able to achieve higher efficiency. So yeah, you can get higher efficiency, but you know, I'm trying to illustrate a point here. I'm just having a basic current source and a basic driver circuit. If I was to build an amplifier, I would certainly look at one of those circuits. My circuit is more like the Death of Zen type amplifiers. If you ever looked at Nelson Pass type circuit, he used MOSFETs, which he has his own argument why they're better. He also has this argument why it's okay to have some second order harmonic in your signal, the way, you know, air pressure is and all that. I'm not going to get into all of that. But I didn't want to go with his circuits either. I wanted to have my own circuit to illustrate, you know, the Class A amplifier utilizing the current source here. Okay, so we got all that out of the way. Let's take a look at the actual built-out circuit. So here is the circuit. Of course, here's the current source part of the circuit, and over here is the driven part of the circuit. There's the small signal transistor driving the power transistor. And like I said, we're going to run it at a lower than ideal current. If you recall, with the voltage here, we'd want 0.75 volts. But you do have to remember, my circuit will never swing to the rails because, you know, you're going to have some losses here. Sense resistor, transistor losses, emitter resistor loss here, of course another transistor. So we'll never get a 12 volt peak to peak in this circuit. So we don't necessarily have to have 3/4 of an amp, 750 milliamps of constant current in this circuit. But at 0.33 amps, it's going to be performing pretty weak. I would be pretty sure of that. And of course, I will adjust this circuit to handle higher current. I'll have to dig up larger heat sinks for that, and we'll see how that performs. Okay, for this circuit, let's fire it up, do the music test, get some scope measurements, see how it works. Well, that circuit's not going to have a lot of gain, so I'm going to have to use the preamp. And of course, I left the amplifier turned on for a day or so, and it kills these crappy so-called heavy duties. I'm not even sure if they're really heavy duties or just the carbon zinc type. But I found a good deal on alkaline batteries, which should hold up a little better in the amplifier. I wonder if they make low self-discharge type rechargeable 9 volts. I'll have to look into that one. But anyway, let me get this thing going. Okay, after a couple false starts, I think I got it going. Okay, we have the power supply set up for 12 volts, 1 amp current limit. Getting a little display multiplexing reacting with the camera shutter rate there. So I turn the amp on, and it's drawing 320 milliamps. Alright, I have the music player hooked up, and let's see what it sounds like. And that music was the Woods Band from their Woods Band album. The track is Noisy Johnny. Gay and Terry Woods played in Steel Eye Span on their first album, and for whatever reason they left that group and kind of went on their own and cut their own album. Didn't really go anywhere, but it's still pretty good music. More of that folk revival stuff I like to listen to. So that's my little music vignette for the video. Okay, back to the YouTube safe music. One thing I notice is, the amp does lack power. It does start to break up when you crank up the volume. So let's give a quick listen. Yeah, I'm not sure how much power we're getting out, but if you notice that, it does start to break up when I turned it up. Well, let's get the scope going here and get some measurements. Okay, I have the 8 ohm load hooked up to the output of the amplifier. And the 1 kilohertz signal going there. It's not an awful looking sine wave, but I need to adjust it to the maximum point before clipping. And we gotta turn that down a bit. There we go. Yeah, it starts getting a little uneven looking, as there's going to be harmonics in it. It's fairly close to symmetrical clipping. A little flat on the top there. Let's see, let's tune out that distortion. Let's say probably about there. About 1.76 volts RMS. 1.76 squared divided by 8 ohms. 0.3872. About 400 milliwatts. Not so good. Like I said, running it at lower than recommended current, we are not going to get a lot of power out from this thing. So let's take a look at distortion. So I need more waveforms on the screen. And then turn that off. And tune that up. Oh yeah, lots of distortion. Here's the 4.5 kilohertz pilot signal that I add. I'm getting a huge second harmonic. See if I can tell how much that is. See, that's like 0.75 of a graticule there. So that would be 3, 6. Yeah, there's probably around 8 or so. And we have some third harmonic as well, about 3%. Now, this type of Class A amplifier with not a lot of feedback, it's going to have a lot of distortion. Really need a lot of voltage gain to have something to feed back to reduce that. But let's see. You can see the waveform doesn't look really symmetrical. But if I reduce the signal, reduce that, turn that up, we'll turn that off, and much improved. So now there's pretty much just second harmonic, about 2%, and really nothing else. So it should sound fine at lower output levels. Okay, so what I'm going to do now is increase the current, rebias the amplifier, and of course I got to find some heat sinks for it, bigger heat sinks, and see how it performs with more current going through it. Well, here is the completed schematic of the amplifier with the changes. What I did is change this 2 ohm resistor to a 1 ohm, and I rebiased the amplifier. This is a 2.4K resistor. I actually had to parallel a 2.7 and a 22K to get this value. The reason for that is I wanted to get the clipping as symmetrical as possible so I can get as much power from this thing as I can. And I just clipped on pieces of aluminum to dissipate the heat. And it's doing what Class A amplifiers do, getting nice and hot, even though it's sitting here idle. So what I want to do now is check the output, see if we're going to get any better output. Okay, so I'll adjust this, get rid of the clipping. He's clipping there. Let's turn this down. Yeah, it's fairly symmetrical, not perfect. About 2.68 volts RMS. So let's see what that is. 2.68. 0.8978. We'll just say 0.9. It's so close. So yeah, we're doing much better there with the output just by giving it some more current. Giving it the current it needs. Let's check the distortion. Oddly enough, distortion is better. See, that's our pilot signal. And our second harmonic is only at 2% now. We have a third at about 1%. But that's at maximum output. Let's drop that back. Turn this on. Okay. As I dial that back, look what happens. This is our 1% again. So this has dropped to, I don't know, about 0.5, 0.6. Third harmonic's gone. There's no other harmonics. And you know what they say, the second order harmonic is the least offensive to the sound. And it's fairly small. So this amplifier is working much better now that we're giving it a lot more current. And so how does it sound now? Okay, to wrap up this video, I'm going to answer some questions I think will potentially be asked. But before I get started on that, I want to mention that I did change the value of this capacitor. On the schematic, I had 2.2 microfarads. I never used that in the circuit because this has low impedance input. The design of this amp is quite low, and a small value cap would roll off your bass. So I put a 33 microfarad capacitor here. The first question that might get asked is distortion. Why did this amp have distortion? Well, you've probably heard that some audiophiles like Class A amplifiers because they don't have crossover distortions. In the Class A design, the transistors are turned on for the full 360 degrees of the waveform. In a push-pull type amplifier, you have the upper transistor handling the upper part and the lower transistor handling the lower part of the circuit. And at the crossover point, the transistors hand over current to the opposite transistor. Well, again, in the Class A amplifier, that's not happening. These transistors are always turned on. So there is no crossover distortion. Crossover distortion is very damaging to the sound because it produces higher order harmonics, which are quite audible. Does that mean your Class A/B push-pull amp is bad? Absolutely not. A good design amplifier is biased just right, so the crossover distortion is eliminated. But there is still a handoff of current taking place, and the Class A amplifier does not have to do that. So what about the lower order harmonics we saw with this amplifier? Well, lower order harmonics, as I said, is much less damaging to the sound, but you really should have those cleaned up in a good amplifier circuit. This amplifier does not have a lot of voltage gain. You need to have a lot of voltage gain in order for negative feedback to do its job. This does have a little bit of negative feedback. You have this resistor here, emitter resistor here, but it doesn't have a lot of gain, as I say. I would need some upfront stages giving me some higher voltage gain for this circuit. Then I can bring some global negative feedback around and that would linearize the amplifier and clear up that distortion. What about the output power? Can I get more power from this amplifier? Well, I didn't film it. I did try running this amp at 850 milliamps, and I did not get any gain of output. The reason being is, I could have 100 amps through here, but with my limited output voltage swing, you're only going to get so much current through an 8 ohm load. Yeah, you could use a lower impedance and then you can get more power, but I wanted to design this for 8 ohm loads, and with that in mind, I pretty much had enough current and was able to get just shy of 1 watt. And to be honest, that's not real bad. A lot of integrated circuit amplifiers that are optimized for 12 volts to get as much power out as possible, they'll do around 1.5 watts. So, we're not too far behind. You might be saying, well, didn't you test amplifiers that were putting out like 7 watts using a 12 volt supply into 8 ohm loads? Well, those were bridged. When you bridge an amplifier, you, in theory at least, get 4 times the power. These amps are output, load to ground. They're not bridged. Another question that might come up is, when I reduce this resistor here from 2 ohms to 1 ohm, this is our sense resistor, why didn't the current double? Well, it almost doubled. We went from 320 milliamps when it was 2 ohms to 600 milliamps. Why didn't it go to 640? And that's probably due to the increasing current in the resistors causing the gain to drop. And I could attempt using a lower value resistor here that would let more current flow in the circuit and turn the current to that predicted value. And what is the efficiency of the circuit? Well, with a fixed current source, we figured that 25% is as good as we're going to get with this Class A amplifier. Well, I got half again of that. So if we take our 900 milliwatts divided by the total power the circuit consumes, which is 12 volts times 600 milliwatts, that's 7.2 watts. So we ended up with a ratio of 0.125, which converted to percent is 12.5%. Can I get any better? Sure, I think so. If I redesign this amp by changing these 1 ohm resistors to something less, we'll have less loss in these. We will gain some efficiency. Right now, these 2 resistors are consuming a total of 720 milliwatts. And another thing is, at the output power I'm able to get from the circuit, I have too much current. And that's easy to figure. 900 milliwatts dissipated from an 8 ohm load, it's going to require a peak voltage of 3.8 volts divided by that resistance. I'm going to need a little less than half an amp. So if I set this amplifier for half an amp instead of 600 milliamps, the total consumed power will go down and the output power should remain the same. So again, we'll increase the efficiency that way. Probably get the circuit up to close to 20%. But because of losses, you need some losses. You have to have a sense resistor and this emitter resistor to help stabilize the thermal and DC parameters and reduce some of the AC distortion in this amplifier stage here. Well, that'll about do it for the Class A amplifier with the fixed current source. The next amplifier design will have a similar Class A design with a coil or a transformer instead of a current source. We'll see how that works. But I want to spread these videos out a little bit, so I'll do that one a bit later. I want to put up some other video topics as well. Kind of keep it interesting for everyone. Well, that'll wrap it up for this. Thanks for watching.